Hi everyone, welcome back to the Comptia Network Plus course. SYN Flood. A SYN Flood is also a DOS attack that inundates the receiving machine with lots of packets that cause the victim to waste resources by holding connections open. In normal communications, a workstation that wants to open a transmission control protocol, internet protocol, TCP/IP communication with a server sends a TCP/IP packet with the SYN flag set to 1. The server automatically responds to the request, indicating that it's ready to start communication with a SYN sync acknowledgement. In a SYN flood, the attacker sends a SYN sync, I suppose. The victim sends back a sync acknowledgement, ACK, and the attacker leaves the victim waiting for the final ACK, which means acknowledgement. While the server is waiting for the response, a smaller part of the memory is reserved for it. As the SYNs continue to arrive, memory is gradually consumed. Figure 14.4 shows an example of a simple DOS SYN flood attack. So here in figure 14.4 we can see attacker sends multiple SYN requests to a web server. Web server responds, SYN ACK replies. Web server waits to complete three-way handshake. A valid user sends SYN request. Web server is unavailable, SYN flood. You can see that the preyed upon machine can't respond to any other requests because its buffers are already overloaded and therefore rejects all packets requesting connections, even valid ones, which is the idea behind the attack. The good news is that patches to help guard against this type of attack are available for the various network operating systems today. Reflective amplified attacks. Reflected or amplified attacks increase the effectiveness of a DOS attack. Two of the more effective of these types of attacks involve leveraging two functions that almost all networks use, DNS and NTP. In the next two sections, these attacks are described. DNS. A DNS amplification attack is a form of reflection attack in that the attacker delivers traffic to the victim by reflecting it off a third party. Reflection conceals the source of the attack. It relies on the exploitation of publicly accessible open DNS servers to deluge victims with a DNS response traffic. The attacker sends a small DNS message using the small victim's IP address as a source to an open resolver. The type of request used returns all known information about the DNS zone, which allows for the maximum level of response amplification directed to the victim's server. The attack is magnified by recruiting a botnet to send small messages to a large list of open resolvers, DNS servers. The response from the DNS server overwhelms the victim, as shown in figure 14.5. So here we see attacker controlled botnet, small spoofed DNS request, amplified DNS response from open resolver, victim's eCommerce server. NTP. While NTP reflection attacks use the same process of recruiting botnets to aid the attack, the attacks are not reflected off DNS servers. They are instead reflected off network time protocol NTP servers. These servers are used to maintain time synchronization between devices in a network. The attacker and his bots send a small spoofed 8-byte UDP packet to vulnerable NTP servers that request a large amount of data, a megabyte's worth of traffic to be sent to the DDoS's target IP address. The attackers use the moonlist command, a remote command in older versions of NTP that sends the request a list of the last 600 hosts who have connected to that server. This attack can be prevented by using the leased NTP version 4.2.7, which was released in 2010. ARP Cache Poisoning. ARP Cache Poisoning is usually part of a man-in-the-middle attack. The ARP cache contains IP addresses to MAC address mappings that a device has learned through the ARP process. One of the ways this cache can be poisoned is by pinging a device with a spoofed IP address. In this way, the attacker can force the victim to insert an incorrect IP address to MAC address mappings into its ARP cache. If the attacker can accomplish this with two computers having a conversation, they can effectively be placed in the middle of the transmission. After the ARP cache is poisoned on both machines, they will be sending data packets to the attacker, all while thinking they are sending them to the other member of the conversation. Packet protocol abuse. After an attacker has broken into the system, attained access, and escalated their privileges, it is important for them to maintain their authority on the system so they can access it at a later time. They could put an operating system backdoor on the target, but in some cases the firewall on the victim may not allow outgoing TCP connections. One of the ways in which a hacker can get traffic through a firewall that would typically not be allowed is by concealing one protocol within another, which is a form of tunneling. TCP can be encapsulated into either DNS or ICMP, thereby passing the firewall restrictions. An example of this is using a program called Iodine to encapsulate IP traffic in DNS packets. Once the DNS packets reach the local DNS server, they are forwarded to a second machine running Iodine that de-encapsulates the packets and send them onto the attacker. The DNS traffic is allowed by the firewall and is able to reach the client. In this way, the attacker is able to communicate with the victim machine. This process is illustrated in figure 14.6. So I suppose here we have server running Iodine, local DNS server, DNS traffic encapsulated, DNS traffic encapsulated, server running Iodine, IPv4 traffic, internet. Spoofing. And IP spoofing is a process of changing a source IP address so that one computer appears to be a different computer. It is usually done to get traffic through a firewall that would not normally be allowed. It may be used to access a server to which the hacker would normally be disallowed access by their IP addresses. While IP address spoofing may be the most well-known type of spoofing, it's not the only type used by hackers. The following forms of this subterfuge also exist: ARP spoofing, discussed earlier in this section, ARP cache poisoning; refer spoofing, in which the refer header of an HTTP packet is changed to reflect an allowed referral page which some sites require for access; email spoofing, in which the from field is changed to hide the true origin of an email. In most cases, this is to conceal the identity of an email spammer. Brute force. A brute force attack is a form of password cracking. The attacker attempts every possible combination of numbers and letters that could be in a password. Theoretically, given enough time and processing power, any password can be cracked. When long, complex passwords are used, however, it can take years. Setting an account logout policy is the simplest mitigation technique to defeat brute force attacks. With such a policy applied, these accounts become logged out after a set number of failed attempts. Session hijacking. Session hijacking attacks attempt to take over a user's session with a secure server after the user has been authenticated. This can be done in the following ways. Session fixation. The attacker sets the session ID ahead of time by sending a link to the victim with the ID preset. When the user connects, the attacker awaits for the authentication to complete and takes over the session by disconnecting the user and using the ID to reconnect. Session sidejacking. The attacker uses a sniffer to steal a session cookie from the user. Alternatively, if the attacker has physical access to the user's machine, they can steal the session key from the memory. Cross-site scripting. The attacker uses the user's computer to run code on the site that may allow him to obtain the cookie. The attacker does this by putting malware on the user's computer. The malware runs the code on the site after the user authenticates to the site. So I'm going to leave it today for this video. If you like listening, please consider sharing and subscribing. Thank you.